In the beginning, there existed an incredibly dense and compact mass of matter. This mass eventually underwent a massive explosion, what we now refer to as the Big Bang, which led to the creation of atoms, molecules, stars, and galaxies that populate our universe today. For decades, physicists have embraced this model as the leading explanation for the origin of the cosmos. However, recent scientific developments have introduced alternative theories that challenge the idea of a singular beginning. Some researchers now suggest that the universe may not have originated from a single moment of creation, but rather exists within an ongoing cyclical process of expansion and contraction, possibly repeating infinitely. One prominent voice adding to this discourse is physicist Brian Cox, who has questioned the conventional Big Bang model by raising a philosophical dilemma. How can something emerge from nothing? His skepticism adds a compelling layer to the scientific conversation. Supporting this shift in perspective, data from the James Webb Space Telescope has uncovered observations that appear to conflict with the notion that the Big Bang marked the absolute beginning of everything. If this pivotal event wasn't the universe's true starting point, then what was? We invite you to explore this fascinating frontier with us as we delve into the origins of the cosmos. Together, we'll examine emerging theories that challenge traditional thinking and seek answers to some of the most profound questions in physics. To stay informed on the latest discoveries and theories about the universe, consider subscribing to our channel, liking this video, sharing it with others, and enabling notifications. According to the Big Bang theory, our universe began approximately 13.8 billion years ago. At that time, it was incomprehensibly small, hot, and dense, possibly no larger than a peach, and possessed a temperature exceeding a quadrillion degrees. In just minutes, the fundamental elements that make up our world were formed. Remarkably, this theory aligns closely with current astronomical observations, including cosmic background radiation and the abundance of light elements such as hydrogen and helium. These consistencies make the Big Bang theory one of the most well-supported models in modern science. Yet despite its success, the Big Bang model is not without its gaps. It offers no detailed explanation for the earliest instance of the universe's existence. This limitation arises because our current physical theories, specifically the combination of general relativity and high-energy particle physics, are inadequate when applied to such extreme conditions. As we trace the universe's evolution, back to its origin, we encounter a mathematical singularity, a point of infinite density where the known laws of physics break down. This concept is problematic and suggests that a more complete theory is needed to truly understand the birth of the cosmos. To address these challenges, physicists are exploring new realms of theoretical physics. One of the most promising approaches is string theory, which attempts to unify gravity with the other fundamental forces of nature under conditions of extreme energy. Within this framework arises the concept of the ekpyrotic universe, a term derived from a Greek word meaning conflagration or cosmic fire. This model posits that the Big Bang was not the beginning, but rather a dramatic transition in a much longer, ongoing cosmic cycle. This idea leads naturally to cyclic cosmology, a theory proposing that the universe undergoes an eternal series of expansions and contractions. Although the concept of a cyclic universe has been around for centuries, string theory now provides it with a rigorous mathematical foundation. According to this view, the universe oscillates endlessly, each Big Bang being a renewal rather than a creation. Renowned physicist and Nobel laureate Roger Penrose has contributed significantly to this field with his own model of a cyclic universe. Penrose noticed a fascinating mathematical similarity between two extreme states of the cosmos: the early universe, which was hot, dense, and small, and the distant future universe, which is expected to be cold, expanded, and nearly empty. Through a mathematical transformation known as conformal rescaling, Penrose demonstrated that these two apparently opposite states might actually be equivalent in structure. This suggests that a universe devoid of matter might eventually give rise to a new, dense universe, a counterintuitive but mathematically consistent idea. From this perspective, the end of one universe, characterized by the evaporation of black holes and the dispersal of energy, could seamlessly transition into the birth of a new one. What appears as nothingness in this final state might still contain the seeds of a future cosmos. Interestingly, under these extreme conditions, our traditional notions of size and time begin to lose their meaning. The cold, empty end of one universe and the hot, dense start of the next are connected not by conventional time, but by a deeper geometric symmetry. In Penrose's cyclic model, the causal relationship between the end of one universe and the beginning of the next doesn't follow a traditional timeline. Instead, both states exist in separate temporal frameworks, which makes the model fundamentally different from linear time progression. This blurs the line between physics and philosophy, raising profound questions not only about the nature of time and space, but about existence itself. How did these cycles originate in the first place? This leads to one of the most enduring metaphysical questions: why does something exist rather than nothing? Within the realm of physics, there are three primary possibilities for the origin of these cosmic cycles. First, it's conceivable that there is no physical explanation, that the cycles simply are. Second, the cycles could form an infinite sequence, with each new universe influenced in some way by the previous one's final quantum state. Third, the universe might exist as a single repeating cycle in which the end somehow contains the conditions necessary to begin anew. These hypotheses are attractive because they avoid the problem of uncaused events and offer a self-contained explanation within a physical framework. Penrose's interpretation of quantum mechanics plays a central role here. In quantum theory, a system can exist in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose extends this idea to his cosmological model, suggesting that random quantum events within each cycle create subtle differences from one universe to the next. This concept offers exciting possibilities for experimental science. If true, it might be possible to detect faint anomalies in the cosmic background radiation, subtle signatures left behind by previous cycles. These clues could help us determine whether the Big Bang truly marked the beginning of time, or whether it was simply one phase in an eternal cycle of cosmic rebirth. Let us know your thoughts in the comments. If you enjoyed this exploration of cosmic origins, don't forget to like the video, subscribe to our channel, and share it so others can. Join this fascinating journey through space, time, and the ultimate nature of reality.